Hello, everybody, and welcome to episode 51 of I Wish You Were Dead, a podcast about things that used to be alive. My name is Mike, and that is Gavin. Gavin, Syracuse just won in double overtime. I'm feeling pretty good.
Yeah, and as much as I consider myself a Syracuse fan, I didn't even know they were playing today. We were just talking about this before we started recording, but it's been a couple of years since I've paid attention to. I used to be really into college and NBA basketball, like to the point where I went to at least one Syracuse game a year for like 5 or 6 years.
And while Syracuse was probably the largest big city around you, it wasn't like you were right nearby.
No, it was like an hour, a little over an hour.
Exactly.
But yeah, from like, probably like 2012. Yeah, maybe like 2011, somewhere around there. And then for 5-6 years after that, I went to at least one game a year, and that doesn't include us going to like the first practice of the season. I'm sure a lot of different schools do this, but they have like an open practice. We can come and watch them play. They have different vendors and stuff there. I think it's called like
Midnight Madness.
Yeah,
Midnight Madness. Yeah,
and so
it's a lot of fun as long as no one's getting stabbed.
Yeah, that happened one year, and then they charged the next year. It was free. Right. I think it was like somewhere between $5 and $15, somewhere around there.
Yeah, it was supposed to be cheap, but yeah, just to try and keep
That was the last year that we went. Was that that year that they charged?
Understandable.
Well, not because they charged, but because Syracuse has gotten worse since then.
Yes, it's been sort of a slow and non-linear path downward over the last decade or so for Syracuse Orange. But who's on their way up? The New York Mets. They just signed a pitcher,
and on that note,
$43 million a year.
Let's move on and not talk about. I was
going to try and hijack this into a sports podcast, but
the inferior New York baseball team.
All right. Are we trying to fight now?
Yeah. Anyway, so before we get into this episode, we actually have a couple of
programming notes.
Yeah, so we actually recently got left a message through.
Didn't know that was possible.
Yeah, so the podcast, a little behind the scenes fourth wall stuff. The podcast is hosted on Anchor.fm. There's a pretty large variety of different podcast places where it's like you upload your podcast to that one service, and then they distribute it to wherever you listen to this, whether it's Apple Podcasts, Spotify, wherever.
Gavin, do you want to guess why we chose Anchor.fm?
I'm guessing it was the cheapest.
Not only is it the cheapest, it's free.
Ah, perfect.
And it's nice. It works well.
Yeah, I mean, it gives us, it's not like we need a ton of like analytics or things, which they give us pretty good analytics for being free.
Exactly. I have no complaints at all about Anchor.fm considering what we're trying to do here.
Yeah, absolutely. And so a new feature that we discovered, actually somebody discovered it for us, is that you can leave us voice messages. So if you go to Anchor.fm, or actually we'll put it in the show notes, our podcast page, and if you want to leave us a voice message, please be nice to us, or at least don't be vulgar, and if you do, we might include it in an episode. Who knows? So my old grad school advisor, speaking of which, the day we're recording this is actually his 50th birthday, so happy
oh, you're kidding.
Yeah, happy slightly belated birthday, Darren. He left the show a voice message, among other things, mostly saying stop bad-mouthing camels.
That was his main point.
Yeah. So the groups that he works with is not like exclusively camels, but he does work a bit with camels. And to that I say no.
Wow. Okay.
I'm not going to stop bad-mouthing camels.
We're like 4 minutes into this podcast, and you're just making enemies left and right, Gavin.
Yes, I am. But he said, a variety of other things, but I didn't reach out to him or didn't have time. I was pretty busy in the couple days since he left that message. I actually reached out to him to be like, hey, can we include part of this in the show? Otherwise, you would have just heard him. But no, I will not stop hating on camels. We will do an episode about camels at some point for sure. And we may potentially have a guest for that. Uh,
I have an idea who that might be.
Yeah. So if you feel so inclined and would like your literal voice heard on the podcast, feel free to leave us a voice message.
Yeah, this is the now explicit warning. Now that we know this exists, if you leave us a voice message, that is also you telling us that you are allowing us to play it on the actual podcast.
Yeah.
Because we don't have that permission now, we are not playing the one voice message that was left to us thus far.
Absolutely. And then one really quick programming note just from me before we get into the actual content of this episode. So I realized, because I have been going back through and with uploading all the stuff to YouTube, I've realized that considering we're a science podcast, we don't tend to cite our sources that often. Which is on me, because I'm the one who writes the scripts for these episodes, more or less. And so that's something that we're going to be better about. In the show notes, I'm going to be leaving Mike at least starter links to get you started if you want to look into more things. And then probably over the next couple of weeks, I'll be going back in and sort of retroactively be adding sources to older episodes. So if you have an episode that you're particularly interested in, give it about 2 weeks and then go back and you take a look at the show notes and that, and you'll find some good links to get started if you want to look more into a particular topic.
Yeah, that is definitely something we should have been doing from the beginning, but there's no reason, there's no reason not to start now.
Yeah, exactly. So in the show notes, you'll find, at least, like I said, starter links, nothing super technical. Maybe I'll do a majority not super technical and then one or two that are more technical if you feel like getting in the weeds. But speaking of this episode, there were no weeds at the time that we're talking about today.
Ooh, was that a transition?
It was a transition. It's pretty smooth, right?
Well, before you do that transition, do we want to give a quick preview of next week's episode, or do we want to leave it as a surprise?
No, we're just leaving that as a surprise.
All right, so tune into next week's episode. It's a surprise.
It is. It is our podcast 1-year anniversary. I'm not going to spoil what the topic is, but I've been working on it for over a month now, probably. Yeah, so I'm super excited for it
at this point. I think
I'm very excited for it. So keep an eye out for next week's episode. Anywho, now that it's starting to get a little colder out, not as much where I am because I'm currently back in the desert.
Thanks for reminding me.
Yeah, but I'm not in my blanket fort. This hotel room that I'm in this time is different and doesn't need the blanket fort. But my mom actually just sent me back home in New York a nice little video of some snowfall today, and Mike, living in the Syracuse area, which is very famous for its snow and cold. I'm assuming that it's rather cold there right now.
So I've been referred to as a polar bear at many times. As of right now, it's hanging around 30, 32 degrees, which for me, I look at that, I'm like,
that's not too bad.
It gets 50 degrees colder than this around here.
Yeah.
We can't be saying it's cold yet. So most people would say it's cold. I am.
You're a true Syracusean.
If you let the cold know that it's getting to you now, it's going to bury you by January. That's been my philosophy.
Well, now that it's getting sort of cold-ish,
it's getting colder.
Let's talk about advanced cold.
Ooh.
So today we're going to be discussing a period/periods of Earth history that is colloquially known as Snowball Earth.
What's it officially known as?
We're going to talk about that.
All right, we're going to get there. I'm looking forward to it.
Mike, just based off of the name, Snowball Earth.
We're doing this. Damn it. All right.
I know you thought you could escape it, but no, you can never escape me. So what? Just based on the words Snowball Earth, what do you think that entails?
So, my best guess would be that the either polar ice caps or, the Antarctic line and the Arctic line or something along that line, are just significantly further down in terms of lines of latitude than they are today. Would be my best guess. I'm assuming that at the equator, there's no real time where there's any regular snow or frozen water throughout Earth's history. But if I had to guess, when we're talking about Snowball Earth, we are talking about regular periods of freezing temperatures and frozen water, significantly closer to the equator than we have now.
That is sort of correct.
That's my brand.
Well, I thought it was actually really funny in you saying that. I don't think there was ice at any point at the equator in Earth's history.
Are you gonna tell me that's wrong?
We're going to talk about that a lot today.
Oh boy.
And so also a quick correction to something that a lot of people don't seem to understand. Because you mentioned like you said, the Antarctic or Arctic line.
Yeah, that's a topic
I think are you
with.
talking about the like Arctic Circle?
Yeah, I think that's what I'm referring to.
So the Arctic Circle and the Antarctic Circle are lines of latitude at, I believe, 67 degrees north for the Arctic Circle and 67 degrees south for the Antarctic Circle. Those don't have actually anything to do with ice. Those are daylight stuff.
Oh, okay.
So it's basically if you are north of the Arctic Circle or south of the Antarctic Circle, that is the sort of the cutoff for in that hemisphere's winter. You start to get periods of longer than 24 hours without any sunlight.
And in the summer,
you get yes. So that's just sort of the cutoff for when you start to experience that going full days without sunlight or without sunset.
I feel like that's something I knew at one point and just clearly forgot, but that makes total sense.
Yeah, and that just is up to the tilt of the Earth. That's not anything to do with like a climate thing. Yeah. So even way back when the dinosaurs were around, which we'll talk about, there wasn't really any significant polar ice. That still was the same. The Earth's tilt might have been a slightly different than it is today, but there would have been areas at the poles where it was, for a couple of weeks in the winter, it was permanently dark. For a couple of weeks in the summer, it's permanently light. But something that I feel like a lot of people either misunderstand or just like vaguely understand, but not super important to today's conversation. Anywho, Snowball Earth is a hypothesis or collection of hypotheses that at various points in Earth history, it was entirely covered or nearly entirely covered in glaciers. Think Hoth from Star Wars Episode 5.
I have some bad news.
You've never seen it. Okay. More or less extreme glaciers stretching to the equator or really close to it, depending on who you ask, which that phrase, depending on who you ask, will be heard many times.
So does that mean there just wasn't a whole lot of like solid land, and most of like the solid ground on the planet was frozen water?
We're going to talk about that, but first I think it's really important to talk about ice ages in general, because a lot of people know that very recently in Earth's history, and technically today, again depending on who you ask, we are in an ice age. Or there very recently was an ice age. But not many people sort of understand what that actually means. So...
yeah, what does that mean actually, now that you mention it?
All an ice age means, and again, people will quibble on the details about this, but as I understand it, an ice age is just a time where there is permanent ice that is not like on mountaintops. Because mountains as high as like Mount Everest, even if it was at the equator, would still probably have ice on it. If it's, miles, plural, above sea level, that's probably going to have ice on it.
But let me ask, so you said that there's any ice, so like if Antarctica exists, or I get, the Antarctica is partially an archipelago, I guess, of solid land, but like...
No, Antarctica is an entire continent.
Right, but I know there's some like solid land under all the ice, but like if there is any ice at all in Antarctica, that means that we are in an ice age?
So the phrase I used was permanent ice, which means ice that goes more than a year, so it does not melt in the summer, not fully.
Right, so if that ice exists for more than a year, then we are in an ice age regardless of how big it is, up to, I guess, a certain order of magnitude.
Right, and it's like you sort of need to hit like a certain threshold to get like, during your winter you need enough snow for it to be able to keep itself cold, because Some in the summer temperatures in Antarctica do get well above freezing, but there's just enough ice there that it keeps itself cold.
Right.
So basically, if you go multiple years without the ice at the poles melting, that is loosely the definition of an ice age.
Wow.
Which
Wow.
again sounds relatively common because that is all we are used to. Today, both of the poles have a lot of ice on them. On Antarctica, ice sheets can be, a kilometers thick, potentially like up to like a mile thick of just solid ice. And in the northern hemisphere, like the glaciers on Greenland don't get as thick, but, are still probably, a kilometer plus. So, half a mile thick. And so that's all that we've known, but that is actually quite rare in Earth history, because even though like during the time of the dinosaurs, the Mesozoic era, there might have been seasonal ice at the poles. During those weeks or months of not having any sunlight, if you were in the Arctic or Antarctic Circle, it was probably below freezing. But global temperatures were high enough that, when the summer came around, all of that snow eventually melted. So having permanent ice at the poles is quite rare. And in fact, in the Phanerozoic eon, the eon that we are currently in, so basically in the last 541 million years is the start of the Phanerozoic. That has only happened 3 times.
What's only happened 3 times?
Having ice at the poles.
That's just wild to me. That
again, because that we are so used to it, because that is all that we have ever known.
So let me ask a question with regards to that. So in the current time that we've had this permanent ice at the poles, how long has that occurred for? Like, how recent is that?
We'll get there. I'm going to break down those 3 times, just so we get a frame of reference for Snowball Earth, because none of these times are Snowball Earth.
Wonderful. All right, let's get to it.
So the first time in the Phanerozoic that this happened was in the late Devonian period. So this was multiple pulses. So it's not like it just went and stayed. There was a lot of glaciers, and they retreated a bit. Then they advanced and retreated, multiple pulses of it. That lasted for around 10 to 15 million years. And that ranged from, give or take, 372 million years ago to 360 million years ago. So, like I said, max like 15 or so million years.
Mm-hmm.
The next one was in the late Carboniferous period through most of the Permian period. And again, this was multiple pulses, and this time lasting, around 100 million years of this sort of generally cooler temperatures. And this lasted from, depending on who you ask, somewhere toward 360 to 260 million years ago. So there was not a long gap between those two. There was a bit of time during most of the early and middle Carboniferous period where things were pretty tropical, lots and lots of plants, and but very long extended period of generally cool temperatures with permanent ice. That doesn't necessarily mean that there were huge ice sheets getting down toward the equator, though. And the modern glaciations, which, depending on who you ask, go from around 34 million years ago, is when permanent ice is thought to have started in Antarctica. Not so much at the North Pole, but in Antarctica, probably around then, to today. Or if you consider needing both poles to have ice, are probably closer to 5 to 3 million years ago through till today.
So Antarctica had polar ice sheets around 30 to 35 million years ago, but the Arctic didn't have those permanent ones until 3 or 5 million years ago. Is that about right?
Right. And the northern ones I'm a little more iffy on. Those numbers were a little more harder to track down, but that's generally what I was able to find.
Mm-hmm.
But you'll notice there's a roughly 230 million year stretch with no permanent ice. That goes from the late Permian, around 260 million years ago, all the way through the time of the dinosaurs, and then through half of, quote, the time of mammals, to around 34 million years ago. So roughly half of, probably like 40% of the Phanerozoic eon was a completely, straight period of no permanent ice on the planet at all, with the exception of like really tall mountains. But we're not here to talk about that. That is not what we're talking about. That is small potatoes.
Oh.
Considering what we're talking about today. I just wanted to talk about that, considering how rare in general that is.
Okay, so we have some misdirection. All right, what are we actually talking about today then?
I also wanted to find something real quick else before we get into it. So the opposite, I know. So this episode is going to be real weird because it's old and it's very foreign.
That's our brand. Let's make it happen.
Absolutely. So the opposite of an ice age, or it's commonly called an ice house climate conditions, is a hot house or a greenhouse climate condition. And that is basically the other times. There's not really a good name. I'm sure that there is a technical name for like when you're on the cusp of going from one to the other, but generally you're either in an ice house climate condition or you're in a greenhouse climate condition. And these are times where there's lots of greenhouse gases in the atmosphere. We've talked about that, and we're really doing our best. We're no, because we still have the ice. We're doing a really good job at trying to get to a greenhouse.
Okay.
Because we are still in an ice house climate because we have the permanent ice, but we're really trying hard to get to not have that anymore.
Oh boy, gallows humor is one hell of a thing.
So almost everything that we've talked about on this entire show over the past year has been in the Phanerozoic eon. As we talked about in our episode about the geologic timescale, eon is the largest unit of geologic time. I think technically there's like a super eon, but that's not important. So the Phanerozoic eon, like I mentioned earlier, goes from 541 million years ago until today. Snowball Earth happened, depending on who you ask, at several points throughout the Proterozoic eon, the previous one, before the Phanerozoic, which the Proterozoic eon, the Phanerozoic, the current one, like I said, 541 million years. That's a long time. Pretty much everything we've talked about on the show has happened in that time.
Mm-hmm.
The Proterozoic lasts from 2.5 billion years ago until that 541 million years ago. So basically 2 billion years worth of time. This is a major, major portion of Earth history.
And during that whole time, it was Snowball Earth?
No. So it was at a couple of points.
Oh, I'm sorry. Okay, so it comes and goes during that 2 billion year period.
Yes, just like the glaciers have come and gone during the Phanerozoic, they also come and go during this time as well.
I was going to say, I thought you said that this was more of a rare occurrence, and 2 billion years of Earth's history is a lot.
So, because of how old some of these events are, we don't have a ton of really good rocks to tell us about this time. As we've talked about, the farther back you go, as rocks just are around for longer, they can be eroded, they can be subducted down into the planet and be destroyed that way. We could have destroyed them just doing our human building things. So in general, rocks from this old are not plentiful, but we do have some. And the earliest suggested glaciation I think in the planet in general, because as I mentioned, quite rare, and especially with Earth started out very, very hot. The first eon of Earth is called the Hadean, named after Hades, because it was real heckin' hot. So the Proterozoic eon comes after that, and it is cooler, just because the planet is not new. But this first glaciation...
It would be hard for it to get to hotter, exactly. Way to go.
Exactly. And so this first glaciation is named after Lake Huron here in North America. It's called the Huronian Glaciation in the Paleo Proterozoic, so the early part of the Proterozoic. And it lasted from 2.4 to 2.1 billion years ago. If you're doing some quick math, that's 300 million years.
That's a lot.
That's a lot. And around this time also is an event that we will do an episode on eventually, because it's also a very, very important event in Earth history, known as the Great Oxidation Event, which is exactly what it sounds like. Earth's atmosphere received, actually measurable levels of oxygen for the first time ever.
And how does that happen? Is that like plants?
Not plants, but like single-celled photosynthetic organisms. The things that plants came from. And at this time, there were lots of different pulses of oxygen, just like we've talked about with the different pulses of ice. There were pulses of oxygen that would eventually, there was a lot of iron dissolved in the oceans at the time. And for iron's very reactive chemically, which is why things rust pretty quickly. So this iron would suck up all the oxygen that these things were making. And so you had to get rid of all the oxygen dissolved in the oceans before you could actually get free usable oxygen, which took a really long time. But once that happened, these photosynthetic organisms were abundant enough to produce oxygen. And a lot of funky things happen when you just change the chemistry of the planet like that. Because number one, carbon, as we mentioned, in its various forms, are greenhouse gases. Methane is probably one of the worst forms of greenhouse gas. But carbon dioxide is also pretty bad. We had an entire episode about fossil fuels that discusses the sort of the chemistry of that. But when you combine methane and oxygen, this newly available resource, that combines to form carbon dioxide. So you're taking the worst one and turning it into less bad one. So that removes, basically reduces the levels of greenhouse gases in the atmosphere. And then also, with all of these photosynthetic organisms, they're still sucking up the CO2 as well. So they're reducing the amount of carbon in the atmosphere in multiple different ways.
Clarifying question here.
Yeah.
So you mentioned like less bad, and obviously in the context of today, when climate change is, obviously something that we're all concerned with, like more methane is, really bad, and CO2 is still pretty bad.
Yeah.
But is it right to think of these gases as bad or good during this period of time? I know it's easy to contextualize them today.
That's a fair question. Yeah.
Okay.
I'd say if you're wanting to keep the planet warm, they're good. So I would say let me rephrase that a bit. So methane is more effective as a greenhouse gas than carbon dioxide.
Okay.
So by combining the methane with oxygen, that turns the methane into carbon dioxide, which reduces its effectiveness at keeping the planet warm. And then also, all of these things producing this oxygen suck up the carbon dioxide. So you're reducing the effectiveness of the greenhouse effect while also removing carbon in the first place. So both of these things combined had a huge, huge, huge effect on climate, namely dropping temperatures a lot. Very, very quickly as well. And so around this time, glaciers, obviously with this one being as old as it is, over 2 billion years old, we don't have a lot of evidence. We'll talk about the evidence for all of these in a little bit, because they all have the same lines of evidence. It's not like this old one has different evidence. It's just that the same evidence for glaciation in general, just in older rocks. So we'll talk about how we know that these events happened in a bit. But at this time, it is thought that maybe not all the way at the equator, but very close. and temperatures at the equator would be somewhere around freezing, which compared to today is a mighty big shift.
At the equator, they're around freezing.
Yep.
So when we say around freezing, do we mean like literally hovering right around 0 degrees Celsius? Or are we saying, they got down to like, 10 degrees Celsius, or maybe it was negative 20 degrees, or was it really hanging right around freezing?
It was, and granted, being 2 billion years ago, this is incredibly hard to project.
This is all very fuzzy, of course.
Yeah, I am not a climate person, and even the climate people who study this, you can only work with, the data are only so good. If your data aren't very good, your models cannot be very good. So temperatures could have been around freezing or, plus or minus 20 degrees, which is a big swing when you're talking about climate.
Right.
There's a big difference between 20 and negative 20. As somebody from Syracuse, New York could tell you.
Correct.
So that is the oldest one. And the reason I'm just kind of brushing through that one just because it's the oldest and we have the least evidence for it. We know a glaciation happened, but we don't know a ton of the details. So that's the oldest one. And the longest one, like I said, 300 million years. Back 300 million years ago from today, mammals did not exist. Birds did not exist. Reptiles barely existed. You would look in the oceans and see lots of weird, funky things. The planet would be almost unrecognizable if you were to time travel back 300 million years ago. And that was just this entire chunk of the planet being, depending on who you ask, mostly or entirely covered in ice. And that's not to say that the oceans froze completely solid. It's not like a lake or something that can freeze solid in the winter, just like a layer of ice across the top of the entire ocean.
Okay.
The ones that are talked about a lot more in terms of Snowball Earth are ones in the Neoproterozoic, which is sort of the last part, right before the Cambrian period, which we talked about last episode. So not too long before that. So roughly, they talk about two major glaciations. One is called the Sterteon Glaciation, which was hovering around 700 million years ago. 715 to 665 million years ago. And the Marinoan Glaciation, which was a little more recent, 650 to 635 million years ago. These glaciations, especially the second one, the Marinoan Glaciation, it is proposed by some people, this is very highly argued, that the entire planet was covered in a shell of ice. Basically like, what are those like toys that you used to get as a kid that then got like outlawed in the US for some reason? Like Kinder Balls?
Oh,
Wonder
chocolate?
Balls?
Oh, yeah. Wonder Ball with the prizes inside.
Yeah. So you know how is that really thin shell of chocolate?
Yeah.
That, but ice.
Dude, you're hitting a nerve for me right now. Okay.
I know. I love Kinder Balls. Anywho.
Wonder Balls.
I think they're made by the Kinder, like...
Is it like Kinder Eggs?
Yeah, I think I'm same Googling company. That. Anywho.
Yeah, okay, so there's Kinder Eggs and then Wonder Balls. Wonder Balls.
So, Jesus, Mike. So, the biggest question is, how did this happen? I sort of talked about it a bit with the older one because that one's not as controversial. We know that oxygen increased a lot at that time. We know the effects that has on the climate. But by this point, the oxygen was already there very solidly. So it's like, what was the mechanism that this happened under? And we mostly know from climate modeling, which has errors for sure. And I don't personally understand climate, like I said. So I'm taking all of this from people who know more than me. And as with every event that we've talked about so far in Earth history, whether it's an extinction, whether it's, a radiation of life, there's never one cause. like we talked about with the dinosaurs going extinct, it was not just big rock hits Earth, everything dies. There were lots of other stuff going on the planet too. And that's true with this time as well. So the first thing that is pointed out about this time is that the sun was weaker than it is today.
All right, how does that work?
Like, how do we know that, or what do you mean?
Both. Like how is the sun weaker? Like how does that physically work? And then like follow up to that, how do we know?
Those are questions for smarter people than me.
Okay.
So I to the best of my knowledge, and again, I'm not a physics person. I don't understand almost anything about space stuff. But as the sun fuses more of its material, it has sort of less energy to burn, so it has to burn more energetic material. So the way the sun works is it fuses hydrogen into helium, and then combines, heliums into other things, combines some hydrogens with some heliums, and I think it exerts more energy or produces more energy when it no longer is just doing hydrogen to hydrogen. And
okay.
So that's how I understand it. That may or may not be correct. So I will find a source for that and put it in the show notes.
Okay.
But so for the first one, the old one, it is estimated that the sun was 16% dimmer, 1.6% dimmer than it is today. And for these two glaciations, the more recent ones, it was around 6% dimmer, which doesn't sound like a lot. But when you're talking about the sun,
yeah, right. That's rather
a lot. Yeah. So that's definitely a factor. It's not like the factor, but it is something to consider. As for the actual sort of trigger as to, why did it happen at these times and not, 500 million years beforehand? It's been sort of proposed that there might have been a super volcano that, you might have heard about, volcanoes before, or even experienced like a large volcanic eruption, such as like the one in Iceland, sometime in the early 2000s, I think. But large volcanic eruptions produce a lot of ash, which blocks out some sunlight, reflects it back into space, and cools the planet. The larger the volcano, the more ash and dust it produces, and the more it lowers temperatures. It could have been a runaway photosynthesis thing again, like it was for the first glaciation that we talked about there, caused by just a general increase in photosynthetic bacteria, a lot of extra runoff from the continents, providing more nutrients, things like that. That's a possibility as well. Or it could be just a weathering increase, which, as we've talked about before, just sort of the chemical weathering of rocks just sucks CO2 right out of the atmosphere. And sucking CO2 out of the atmosphere reduces temperatures. Regardless of, it was probably a combination of all of those things. But regardless, temperatures got low enough for ice to start forming on the poles. And a really important sort of concept that needs to be understood to talk about these is something called a positive feedback loop. So, do you have an example, or have you ever heard of a positive feedback loop before?
I not only have I heard one, I might totally fail on this. I think I might be able to define it.
Yeah, go ahead.
So my best understanding of this is a positive feedback loop is something that happens that is sort of self-perpetuating. Like the fact that it's happening, it is going to continue to cause, that cycle to continue unless, intervened on by another force. I am trying to think of sort of like an everyday life example of this. And it's, I am sort of failing to come up with one off the top of my head. But just the general idea of a positive feedback loop, the fact that, a reaction is occurring, it is going to cause itself to continue to happen unless acted on by some outside force, is
right.
Sort of my best definition off the top of my head.
Yeah, and that's definitely true. And I'll give an example here because they are very important in understanding these events. So a nice vocab word, maybe an SAT word, is something called albedo, which is basically how reflective Earth is at a given point.
Just really quick, if you're listening to this podcast and you're worried about the SAT, go do literally anything else. You have better things to do.
You have way better things to do.
Go commit crimes as a minor or something. I don't know. That's not an official recommendation. But
yeah, I was gonna say just as a legal matter, we do not condone.
Don't take legal advice from a podcast, but go have fun.
We do not condone crime. Anyway,
you don't condone crime.
Moving on. So
don't do crimes. Don't get caught, at least.
Mike, you're a teacher.
Imagine what kind of teacher I am.
Okay. Albedo is how reflective Earth is. For example, if you've ever driven in a place with snow, you'll know snow is rather reflective. There's a term called snow blindness for when it's just really bright out, because all of the ice in the snow is reflecting that light that would normally be absorbed by trees or grass. And that's a general thing with, rocks are generally, pretty reflective, just bare rock. The ocean is not very reflective, even though you might get glare from it. In general, ocean water is pretty, it absorbs water, light and heat pretty well. So the positive feedback loop sort of comes in that you get some ice formed at the poles. Ice is reflective. So the more ice there is, the more it reflects heat and light back out into space. And the more heat is reflected, the colder temperatures get, which creates more ice, which reflects more light, which reflects more heat, which lowers temperatures more. So basically, the more ice, the lower temperatures, which means more ice can grow. So that is where the positive feedback loop is coming in here. Does that make sense?
Right. And so can you explain, so we have positive feedback loop. Mm-hmm. There's also obviously, the fact there's a positive feedback loop implies a negative feedback loop.
Yeah.
And what does, if you were describing a negative feedback loop, what would be, that example or that definition at least?
Basically, as I understand it, basically something that snuffs itself out.
So basically it can't be self-sustaining.
Right. It would be,
at least not indefinitely.
Yeah, for sure. Okay. And I without having it in front of me, I'm struggling to come up with an example of a negative feedback loop. But I hear Mike Googling, so he'll be back with that in a moment.
Correct.
What do you got for us?
Oh, you asked me that now. So examples. Oh boy. In audio amplifiers, negative feedback reduces distortion, which minifies. That's not a good example. Oh, you keep talking. I'll be back.
Sure. So this feedback loop basically made it so, and these are all computer models, which model climate, which we can never fully input all of the variables into a model. Climate is too complicated for us to fully put in every variable. But with that caveat, this is what it was telling us. Once it got down to about 30 degrees latitude, which for reference is about where modern day Houston or Atlanta is. So not at all north. This is what is, called the American South. Once ice got that low, these models predict that the positive feedback loop would be so strong that the ice would be enough to overcome any kind of warming and would basically just march inevitably to the equator.
So I have some follow-up questions to that, but
okay.
Just real quick, as far as a negative feedback loop, the best example I was able to find was if your body gets colder, that's going to cause your body to want to shiver and warm itself up. And so your body will not get colder indefinitely. At some point it will warm up. And same thing, if your body temperature gets too hot, you will start to sweat and that will cool itself down. So a negative feedback loop sort of has an expiration date. But with the ice itself. So,
Mhm.
okay, so it is kind of past that event horizon, we'll say, of around 30 degrees latitude.
Mhm.
And at that point, there's not much that can stop the ice from going all the way to the equator.
Yes.
I don't know if you've been south. There's
I
not a whole lot
have.
of there's not a whole lot of permanent ice there at the moment, as you
There
might be
sure
very
isn't.
keenly aware. I assume we're going to get there, but like, what happened?
I guess, what do you mean?
So there was ice there at one point,
Mhm.
and the idea is that it's a positive
How
feedback loop.
Mhm.
Yeah, like
We
what broke
we
that
we
positive
we
feedback
will
loop?
talk about how we got
Okay.
to not being a snowball anymore. Um and then so this was actually something that I threw in the notes really quickly afterward. Something that kind of blew my mind, along with the sun being dimmer. And if I were a good podcast host, I would have put this up in that section. But there were no clouds at this point in time.
Wait, what?
At this
You
point,
you can't
it
just throw this every episode. You throw out like 2 or 3 of these that just. But how are there no clouds?
it was too
It was
cold.
everywhere.
Mm-hmm. Well, think about it. If you're having glaciers potentially miles thick in Houston,
Wow.
it's
Look
going to
at
be super cold. And by that, I mean around the equator, it would be about as warm as, like, maybe not summer in Antarctica, which can, these days be up in like the 60s Fahrenheit, but like spring or fall in Antarctica, by which I mean cold.
and there's not a whole lot of clouds coming from the Antarctic region in the spring and fall, I assume.
Right. And so the clouds, all the moisture in the clouds would freeze and fall, and there was just not enough evaporating to replenish them. And clouds are really important in also reflecting, light, and also weirdly trapping heat. They do a weird combination of it, and it kind of depends on what kind of clouds are. It's a whole thing. Again, I don't really understand climate. But clouds, depending on what kind of cloud, can either aid in warming or aid in cooling. Uh, so with there being none, they were not really doing either. So just a factor that I kind of just saw, and I was like, that's a neat thing to include. Um, so again, especially during the Marinoan, the more recent of these two glaciations, uh, which again was sort of centered at around 640 million years ago, people will argue very strongly that there was no open ocean surface at all anywhere on the planet.
Is there like a strong argument against that if people are arguing strongly for it?
So nobody's really arguing that the glaciation happened. Everybody thinks that, like, yes, this is an event that occurred, that
I
there
mean, like nobody's
was,
arguing against it. Like there's no credible argument that it didn't happen.
yeah.
Okay.
But they argue the full extent. Was it fully solid, or was it a little slushy? And we'll talk about that in a little bit.
Mm-hmm.
I'm just constantly kicking this can down the road. So the evidence that we have in general for glaciations, and this sort of broadly applies to these times as well as those other glaciations that I talked about before, even the ones recently, like the one that we have today. So you'll get glacial deposits in tropical latitudes or paleo latitudes, where it was at the time. And so glacial deposits basically, the key characteristic is that they are poorly sorted, which means that it's not like a nice, big grains at the bottom of like if you look at just like a wall of rock, it won't be like big stuff at the bottom, medium stuff in the middle, small stuff at the top. That is what we would call well sorted. And that means that it was deposited, over time. It had lots of time to settle out. Glacial deposits are not like that. They are very poorly sorted, meaning you could get a giant boulder surrounded by pebbles and sand. That is very characteristic of glaciers. You get these things called drop stones, which are very self-explanatory. It's a big rock that was just kind of dropped in a place where it shouldn't be. And commonly, glaciers are really good at picking up rocks and pushing them somewhere else. And sometimes those rocks will get stuck to the glacier, even when the glacier is, miles out to sea. Say a piece breaks off as an iceberg and just sort of floats out into the ocean, it's still carrying that big rock. Eventually, it's going to melt out and just drop. So you'll get these big, big, big rocks where they absolutely should not be. And we have good evidence of that kind of thing from this time. We get some carbon isotope stuff, which isotope stuff this far back is a little rough, but basically looking at the ratios of different isotopes of carbon, you can tell roughly global temperatures, or how much productivity was going on, how much life was doing at the time. And from that, you can sort of interpret that to mean various things about global temperature. This far back, it's not the most reliable, but it's still a tool in the box. And those sort of really highly suggest a decrease in productivity, suggesting a decrease in temperatures. They have these things called carbonates, which is essentially just some funky ocean chemistry going on, which causes carbonate minerals, things like your calcite, which I've previously described as the stuff that gets stuck in your Keurig that you have to pour vinegar into to get out.
Yes.
Normally, limestone is made from that kind of mineral, and limestone typically is made from the shells of dead animals or other organisms like single-celled stuff. That's how limestone's formed today, and for a lot of Earth history that we've had life, that's how they're formed. These carbonates are not formed like that. They're still limestones, but they're not formed from life. Basically, some weird stuff going on with the ocean chemistry that makes those minerals just sort of crystallize out of the water without life doing it for the water. So it's like if you've ever made rock candy at home, which is a fun science experiment you can do if you have a kid, similar process. How the sugar just crystallizes to the stick or the string, whatever you use, that just sort of happens. And then lastly, and one of my favorite lines of evidence is an iridium layer. Have you ever heard of iridium, Mike?
Nope. I mean, let me rephrase it. Probably at some point, but no.
So iridium is an element, and it is very rare on Earth, but it's fairly common out in space. And so there's a layer of iridium from this time, and there's also a very famous iridium layer from the end of the Cretaceous period, from the asteroid that destroyed or what made the dinosaurs go extinct. Asterisk. That iridium layer is presumably from that meteorite. This iridium layer is not from that, because the Earth constantly receives bits of space dust all the time. However, it's so diluted that it's not really that detectable. But this iridium layer essentially is from all of that space dust building up on top of the ice that was then deposited all at once when the ice melted. So it's not from this big single event, it's just the constant buildup, so suggesting that it was unable to be actually deposited for a long time, and this was a proposal that could have prevented it from being deposited.
So do we think this iridium came from space then?
Yeah, absolutely.
Okay. Yeah, because I guess where else would it come from?
Mm-hmm. And so we've talked about some potential causes. We've talked about how extreme this was. And like I said, depending on who you ask, there's a lot of, depending on who you ask here. I'll circle back to that. Sorry, I lost my train of thought. I did not have enough coffee today. How did you just call me weak?
Weak?
Oh, I'm really offended, Mike.
Hey, never had a cup of coffee in my life.
Okay, moving on. So you asked earlier, okay, if this was so crazy, if the Earth was potentially completely frozen, at least on the outside, there still would have been liquid water underneath, but we would have looked much more like, like one of Saturn's moons, where the outside is frozen with some, potentially liquid underneath. It would not look like the Earth we have today. How did we get to the Earth we have today, if that's the case? This is where stuff gets a little weird, because, again, depending on who you ask, this has really different answers, depending on exactly how frozen the Earth actually was.
Oh. This is where that was a point of contention.
This is where we get to the completely solid versus the more slushy side. Because among the people who study this is very, very hotly contested.
Okay. What's the debate here? I mean, I can take a guess, but go for it.
So, like I said, this hypothesis in general is called the Snowball Earth hypothesis. Many people also sort of argue that it should be called the slushball Earth hypothesis.
That's less catchy.
It is less catchy. But it is potentially more accurate, because these people sort of propose that there was a huge amount of glaciation, and it was real cold, but around the equator there was a band of water that was more slushy at the top, where it was more liquidy. Maybe not completely open ocean, but not frozen solid. And the lines of evidence that they have are, some of them are speculative, some of them are from models, some of them are, they would argue, just kind of common sense. Because we have, a concept that we use a lot in science that you probably have heard of, which is called Occam's razor.
Yes, I'm familiar.
So go ahead, Mike. What is Occam's razor?
It's phrased slightly differently, I think, depending on who you are. I think just like in common parlance, it's the simplest answer is usually correct. I think if you were to talk to like somebody that's trying to impress a girl at a party, they would be a little bit fancier, and they were like, the answer that requires the least number of assumptions is usually correct. It's not a scientific answer, but when science doesn't provide an answer, it is sort of like the best thing you have.
So the way it was taught to me, and this was something, circling back to my advisor, that he was very big on, was the definition that we use in science for the most part is that the option with the fewest caveats, the fewest exceptions needed, is usually correct. And so, with that being said, it is much, much easier to achieve a slushy Earth than a solid one.
Is that everywhere across the Earth, or is it like, slushy,
slushy at the equator?
Right, and then probably,
pretty solid as you go north or south.
That seems to make a reasonable amount of sense.
It is just much easier for that to happen because the equator receives, the most amount of sunlight per year, which means that it has the highest average temperature per year, typically. Some weird things, like the Sahara Desert kind of throw that off. But like in general, the equator is more or less the hottest place on the planet. It is also, and this is also really important, much, much easier to come back from a slushy Earth than it is to come back from a solid one, based on climate models. Basically, the amount of...
That kind of makes sense.
Yeah, because the mechanism proposed that most people would probably assume to melt all the ice is an increase in CO2. Just like we see today, CO2, more CO2 in the atmosphere means warmer temperatures. That is one of the easiest ways for the planet to heat itself, is to produce more CO2. Based on climate models, the amount of CO2 that you would need in the atmosphere to come back from a completely solid Earth, with it being that frozen layer even all the way across the equator, is the slush ball advocates would argue is just not reasonable.
And without knowing anything about it, I mean, it just, if something's not completely frozen solid, it will be easier to melt like that.
Right.
It makes intuitive sense from somebody that doesn't know what they're talking about.
Right. And it's like, well, we know, X amount of CO2 increase in the atmosphere corresponds to Y amount of, temperature increase. So like based on how we understand this math, you would need so much CO2 to melt a completely frozen Earth. It basically, the amount required increases exponentially compared to like the amount needed to melt the fully solid Earth is exponentially more than to melt the slushy Earth. And they would argue that in the amount of time that this event lasted, that amount of CO2 could not have built up.
This all seems reasonable and makes sense.
Again, without looking at the actual data, yes.
Right. Right. Just like intuitively, like it would not be hard for somebody to just like, pull up some data, and if the data, points to an opposite direction, then that's fine. Yes, that's the way it happened. But without conclusive evidence either way, this seems reasonable.
Right. And with that, I'm going to sort of push aside the slushball versus completely frozen argument, because even with looking into it, I did not have the time nor mental bandwidth over Thanksgiving to look at all of the data. I will leave sources for you to do that for yourself if you so choose. But in general, how we sort of came back from it, whether it was slushy, whether it was solid, how we came back from it, more or less is that, well, just because the surface is frozen doesn't mean the rest of the planet is, because plate tectonics does not care if the surface.
Okay.
It does not care if the surface is frozen, or if it is slushy, or if it's not frozen at all, if it's completely liquid. Plate tectonics does not really care. So plate tectonics was still happening. And because of this, volcanism, volcanoes erupting, doing their general thing, was still happening. And as many climate change, or at least human-caused climate change denialists will tell you, volcanoes do produce a lot of CO2. Especially given the timescales that we're talking about. So it is generally easier to have glaciers on continents than on open ocean, just because, water melts ice, right?
Yeah.
And so because of that, the glaciers were more prominent on, or at least thicker, on land than they were on the ocean, on the continents. And so these volcanoes increased CO2, and then because the ice was thicker on the continents, that led to a decrease in the chemical weathering of the rocks, which meant that there was, as we talked about before, chemical weathering of rocks absorbs CO2. So if there's less of that going on, that means there's less CO2 being absorbed, which means more in the atmosphere. So volcanoes throwing off a lot of CO2 and not a lot of stuff around to absorb that just led to a lot of it being built up, to the point where even a little bit of the ice around the equator could melt.
And then once a little bit of that starts, do we have another positive feedback loop in the other direction?
We absolutely do. Because, as I mentioned, the water is much more able to absorb heat. It is less reflective than ice, which means warmer temperatures, which means more melting, which means more water, which means warmer temperatures. And basically just as quickly as it came on, Snowball Earth melted. To the point where some people argue it could have taken as little as 1,000 years for ice at the equator to retreat all the way back up to the poles.
So wait, 1,000 years?
That is what some people have proposed. I don't know if I buy that. But that is what some people have proposed.
Okay.
Yeah. So, but because we now have all of this CO2 in the atmosphere, it was really, really hot and lots of CO2 in the atmosphere. And by a lot, I mean up to 350 times what we have today. And I saw some figures that said that would make it roughly 13% of the atmosphere at the time was CO2, compared to, I think, roughly, I think today it's somewhere around 2%. So, yeah, lots and lots of CO2 in the atmosphere, which meant right after this, it got really, really hot. And so this paved the way, wrapping up here. Because this is a paleontology podcast, we're going to talk a little bit about how life reacted to this, but not too much. So because of this basically made it so that atmospheric CO2 and oxygen were both pretty high, because now all of these organisms that did photosynthesis and that may have caused this glaciation to begin with had lots of food, lots of CO2 to do photosynthesis with, to produce lots more oxygen. So this is another event like the Great Oxidation event that was thought to have put in lots of CO2 in the ocean, or lots of oxygen into the oceans and the atmosphere, which is obviously quite helpful for life as we know it today. And all of this glacial sediment was also being dumped into the ocean, which means nutrients for those same photosynthetic things. That this boost in oxygen, this boost in photosynthesis, this boost in nutrients is thought to have possibly influenced the Cambrian Explosion that we talked about last episode, which, as we mentioned last episode, paved the way for life as we know it today.
Yeah, that was kind of the big one. The Cambrian,
quote
what was the
unquote
other term?
Explosion.
It was explosion, or
like
what?
Pop.
Yeah, explosion. Something happened there, and it was a big deal.
It was, and so these glaciations, it has been hypothesized that the Cambrian Explosion would not have happened when it did if not for these glaciations happening.
Wow.
So thanks, Snowball Earth. Very cool.
And thank you, Gavin, for bringing us down that rabbit hole and giving us a little bit better of an idea of what. So you've been using the term Snowball Earth, but is it also fair to call these ice ages, or is that a separate thing?
This is like advanced ice age, like cue SpongeBob meme of this isn't your everyday darkness. This is advanced darkness.
So when people use the term ice age, they're referring to a different thing.
Yeah, like the ice age that we had recently. So I think the last glacial maximum was like 18,000 years ago, 20,000 years ago or so. Right. At most, at least in North America. I'm not quite sure what the glaciers were doing over in Europe, but I think they were more extensive in North America. They made it to like southern New York, maybe to like central Pennsylvania.
So this might be what I was thinking of when I was trying to define Snowball earlier as I was thinking of the ice ages. But okay, so they are two different things that, share a common idea.
Exactly. And it's like even vaguely similar causes, like it is one of the contributing factors to the recent ice ages, which we can do again an entire episode about, is the Himalayas being their mountain building increasing. That's just, as you build really tall mountains, that's a lot more rock to be weathered, which, as we've talked about a couple times in this episode, rocks weathering sucks CO2 out of the atmosphere. And if you have a lot more rocks to be weathered, that sucks out more CO2, which decreases temperatures and can cause an ice age. And that's one of the things, not the thing, but one of the things that is hypothesized to have kickstarted these recent glaciations today. But imagine that on a much, infinitely bigger scale. And that's Snowball Earth.
And that is the episode on Snowball Earth. This has been episode 51 of I Wish You Were Dead, a podcast about things that used to be alive. My name is Mike, and that is Gavin. Keep an eye out next week for our 1-year anniversary episode, which I am very much looking forward to. Take care, everybody, and we'll see you next week.